Welcome to Study Loop.
So a cobalt-60 source that has an activity of 2.6 times 10 to the minus 4 curies is embedded in a tumor that has a mass of 0.2 kilograms. We're told that the source emits photons that have an average energy of 1.25 MeV, and that half of the photons are absorbed in the tumor. So for part A, we're asked to calculate what the energy is delivered to the tumor per second. So the first thing to calculate is the number of decays per second. And we're already given this in Curie, so if we convert it to the number of decays per second, we get simply 9.6 times 10 to the 6 decays per second. So now, energy delivered per second, because half the photons are delivered to the tumor, there's a factor of a half, and then the number of decays per second, 9.6 times 10 to the 6 times the energy of each photon, 1.25 mega electron volts. And then keep doing our unit conversions carefully. We find that this gives us a value of 9.6 times 10 to the minus 7 joules per second. Now for part B, we're asked to find what the absorbed dose is in rad delivered per second. So this is simply going to be total energy delivered per second over the mass of the sample, which if we work it out, works out to be 4.8 times 10 to the minus 4. In part C, we're asked what the equivalent dose is in rem delivered per second if the RBE are for these gamma rays is 0.7. So that tells us that we have a factor of 0.7 to take into account, multiplying our entire expression. And the energy per second per mass is simply the same expression we have above, 4.8 times 10 to the minus 4. So this gives us a value of 3.4 times 10 to the minus 4 REM. Lastly, we're asked what exposure time is required for an equivalent dose of 200 REM. So if we want a dose of 200, and we have effectively 3.4 times 10 to the minus 4 REM per second, we simply divide the two, find that it would take about 6.9 days to receive this dose. And those are our answers.